This stream of water is actually not frozen. Instead, it only looks frozen because the water moves so ideally and perfectly that it never deviates from its original path. In contrast, this water is extremely chaotic. And there's a reason for that. There's one number that determines whether fluids are completely still, called laminar flow, and when fluids are really chaotic, called turbulent flow. But how are these two different types of flows really caused? And what's the math behind it? On a quick side note here, this video was made as an addendum to a video I made almost more than a year ago with one of my friends. And this will be covering some more of the derivations and some more of the conservation laws that we discussed in that video, which is unlisted and I accidentally published, and it's in the description right now. Fair warning, it's a bit more lower quality than some of the other videos I've posted, but it's still a great educational experience, and I even did something hands-on with it, an experiment. Anyways, in that video we talked about the pressure gradient, which we derived, and some aspects of fluid flow, like conservation of mass, and a bit about conservation of energy. In this video, we're going to be talking about the different forces in fluids and how they are arrived. Sorry for the lack of uploads. I've been working on a lot of videos at the same time, so hopefully they're going to release sometime this month and next month. Anyways, back to the video. Around 246 BC, a Greek mathematician by the name of Archimedes was asked by the king to determine if his gold crown was real or fake, alloyed with a different metal like silver. In his time, people knew that gold and silver had different densities. However, the trouble was to actually find the volume of the irregular shape, the crown. Stumbled as he was, he went to take a bath, but when he entered the near-full tub, he realized something incredible. The water that had splashed out when he entered the tub was equal to the volume that he displaced in the water. This way, he could find the volume of irregular shapes, like a crown, by dropping them into the water and seeing how much the water is displaced. By doing this with different masses of objects, he could figure out the density. And in this way, he found out that the crown was actually denser than a block of pure gold, and thus wasn't. But the discovery that an object displaces its volume in fluid led to the idea of buoyancy, and it's the reason why some things float and some things sink. Consider a piece of volume of water in a large container. Since this piece is motionless, it experiences no net force. But there's a force of gravity acting on the water, which is equal to its mass times g. But since the sum of all forces is zero, the force from the neighboring water molecules counteracts this force, producing a force of mg upwards. Rewriting this in terms of v, we get that the total force upward is just the density of water times the volume times g, the gravitational acceleration. But the idea here is we can replace this object with anything, and the force will still be the same, as long as it's the same volume. This force is called the buoyant force, and it's the reason why objects that are less dense than water float, and more dense than water sink. But how does this buoyant force even form? If water acts like a gas, based on my video, there should be a pressure that pushes equally in all the directions. So there shouldn't be a force. But we'll actually find out that the pressure changes with depth, which means there's a preferential direction to which the water pushes towards. The pressure is equal to the force divided by the area it acts on. For an element of water, it feels pressure from all its neighboring elements, but since it has no acceleration sideways, the pressure on all lateral sides cancels out. However, since the water feels a gravitational force, for it to be motionless, the pressure on the bottom must be higher than the pressure on the top, since they have to add up to the buoyant force. This means that the difference in pressure between the bottom and the top times the surface area that it acts on is equal to the buoyant force. But the volume divided by the cross-sectional area is just equal to the height, delta x. So then we can write the difference in pressure between the top and bottom as the density of water times g times delta x, which means we found how pressure changes with the depth. So we found out that buoyancy is one of the forces that could be acting on an object that's in a fluid. But there are actually many ways fluids can interact with themselves and other objects, two of which are important for discussing laminar versus turbulent flow. And the interesting thing is, they're both drag forces, which means they counteract motion. But they have a small difference. If we look at an object moving through a fluid, there are two extreme situations. One, the fluid has no intermolecular attraction and simply bounces off the object. This type of force is called inertial because it's the changing momentum of the particles that affects the object. Second is the viscous force. The momentum of the fluid isn't changed by collisions with the object, rather primarily by friction between different layers of fluid surrounding the object. Let's try to roughly figure out what the force should be in both cases. Let's start off with the first case. Let's consider a sphere submerged in fluid. If this sphere moves at some velocity v, it sweeps out a volume of particles that it interacts with. This volume is a cylinder because the cross-section of a sphere interacting with a fluid is a circle, and the radius of that circular cross-section is the same as the radius of the sphere, which I'm going to call r. And the height of the cylinder? Well, the height is just the distance traveled, which is the velocity times the time increment, which we take to be small, so dt. The total mass of all the particles it hits is just the density of the fluid times its volume, which for a cylinder is just pi r squared times the height, which is the velocity times the time increment, dt. So we figured out the combined mass of the particles the sphere interacts with. But what does the sphere actually do to these particles? Since we're imagining an extreme case with no intermolecular attractions, we can just imagine a stream of particles hitting the sphere, which all bounce off in different directions. Some of the particles bounce straight back, but most of them bounce off at angles. To find the force from the sphere onto the stream of particles, we have to find the average change in momentum after collision with the sphere. So how do we do that? Let's consider the one-dimensional case first. For this case, the angle deflected just depends on the distance from the center of the sphere, which is commonly called the impact parameter if you saw the video on optics. So to find the average angular deflection, we can find the deflection for particles spread out evenly from the distance from the center, and then average those angles out. For the one-dimensional case, it seems like there's a lot more motion in the forward direction. But if we make this particle stream 2D, it's actually isentropic, which means the angular distribution is uniform. That means the average velocity for a particle after collision is 0. Some of the times it'll bounce back fully, some of the times it'll just go through. But even if the particle's velocity never actually is 0, on average, over all collisions, it is. This is because we're looking at the velocity and not the speed. This means the particles, after bouncing off, have an average change in velocity of v minus 0, or just the initial velocity v. Then the change in momentum is just the mass of these particles that come at a time times the change in velocity, which we already calculated earlier, as rho pi r squared times v dt. Then the force, which is the rate of change of momentum with respect to time, is just rho pi r squared times v squared. By Newton's third law, the force on the particles is equal and opposite to the force on the sphere, which means the drag force on the sphere is just rho pi r squared times v squared in the opposite direction, pointing against its motion. So now we've calculated a formula for inertial drag. But what about for viscous drag? What even is viscosity? Well, in the next video, we're going to be going over what viscous forces are and what they're derived from. And in doing so, we'll figure out how to find the forces of viscosity on a sphere, and how that relates to turbulence and laminar flow. To leave you with some closure, on the screen now is an approximate formula for the viscous force on a sphere. So now it's up to you to figure out what conditions you think will make turbulent or laminar flow. And as always, thanks for watching.